Hi everyone and welcome to this continued tutorial in the NPTEL course Machine Learning for Core Engineering Disciplines, and in today's tutorial we will be continuing our journey into unsupervised learning, wherein we will go on to other types of clustering. In the last video we had looked at concepts such as principal component analysis and k-means clustering, and we will now continue that to implement DBSCAN, which is density based spatial clustering of applications with noise, and then we'll proceed on to nonlinear dimensionality reduction techniques like t-SNE and UMAP. So let's go ahead and get started. So in this continued tutorial I want to remind you that we are working with this iris data set, which is a data set of flowers, and there's about 150 data points here. There are 4 different types of features: the petal width and length, the sepal width and length for flowers, and there are 3 types of flowers which we already know, but we are trying to see how much insight can unsupervised learning offer into this simple data set. So having already looked at principal component analysis and k-means clustering, we are now going into a more complex form of clustering, which is density based clustering. So we are looking at the DBSCAN algorithm, which stands for density based spatial clustering of applications with noise, right? And this is different from k-means. So here you don't specify the number of clusters beforehand. Instead you have to specify the maximum distance between 2 samples to be considered neighbors. So it's a slightly different way of working. Instead of the number of clusters, you specify some distance metrics in feature space. However, this can find clusters of arbitrary shape. If you remember, because the k-means clustering works with Euclidean distance and is based on the centroid, we usually get roughly spherical clusters of similar size. Here you can find clusters of arbitrary shape and size because you are not relying on simply the number of clusters in the centroid of every cluster. Now this can identify noise points. So if you look closely at the DBSCAN algorithm, there are ways to classify points as core points and noise points which are on the boundary. So you can identify those points as outliers, and that can be useful in outlier analysis. And obviously, as the name suggests, it is density based and groups points which are together closely packed in high density areas. The key parameters here are epsilon, which is the maximum distance between 2 samples to be considered as neighbors, and then the minimum number of samples which are needed in a neighborhood to form a cluster, right? So these are obviously very crucial parameters, but these are needed, and of course there are several advantages like what we discussed above. Alright, so the first thing is we need to choose this epsilon parameter. So how do we choose it? So what could be done is you can look at a k distance graph which plots the distances to the k nearest kth nearest neighbor for all the points, and then this will tell you somehow how the distances are distributed, right? So what's the distance up to which all points get into one cluster versus for smaller distances only fewer points will be there, and this will tell you what's the right distance beyond which, right, you lose the structural information. So this kind of a plot may be useful, and again you can look like for an elbow where there's a sharp increase which indicates a transition from a dense to a sparse region. And you should also then choose that epsilon at the elbow point which will be most insightful. Alright, so this works because points in clusters have consistent internal density, or at least that's what we want them to have, and points near boundaries or noise, right, or outliers, they show a jump in the distance, right? And finally the elbow, it represents the optimal density threshold, right? So again, this is a heuristic technique. Depending on your data set, you may want a slightly different value. So here what we are doing is we are looking at looking at 10 nearest neighbors, right, and we are trying to find the distances and trying to plot those distances, right? So once you get the distances to the k nearest neighbors, then you are making this plot, right? So this on the y axis is the distance to the 10th nearest neighbor, and here you have however many points you are able to find, right, within that distance. So if you're looking at larger and larger distances like 2.25 here, then you see that almost all the points, right, the data set has 150 points. As you know, this is about 120 or something here, and you are able to see that right at this threshold almost all the points in the data set are included. So we can look at a distance somewhere here around 1.25 or something, where there is a sharp increase in the number of points. So that's the transition from the dense to sparse region as the distance rapidly goes up if you want to look at more neighbors. Alright, so using that information, right, let's choose epsilon as 1.25. that's what I told you from this elbow plot here, where the distance to the 10th nearest neighbor rapidly increased, right, at this point. Alright, so based on that we are capturing the main density regions as the clusters, and then the sparse regions have been separated by the boundary points. And of course, as always, there is a balance between too many small clusters and too few large ones, right. So if you have too few clusters, you don't get insight, and if you have too many, then every point is its own clusters, you don't uncover the similarities in the data set. So from sklearn.cluster, I am importing this DBSCAN module, and again first you have to apply the DBSCAN, right, to find out how the clusters have to be done, and you will be able to specify the epsilon parameter as well as the minimum number of samples which we have done here. Okay, so in this case DBSCAN found two clusters, and there were one noise points, right, and this is actually what we also saw when we did PCA, right, as well as k-means clustering, that only one type of flower was very effectively distinguished, the other two types of flowers were quite close to each other in terms of clustering. You saw that here, right, we discussed that there's really no way to make out the difference between these two clusters, whereas the first cluster is very nicely separated, and that's again what you are seeing here, that DBSCAN is telling us that there are only two clusters here, right. So this could mean that we want different types of features. The features that we have chosen, they may not be sufficiently insightful to tell us the difference between these three types of flowers, and this is where feature engineering comes in. It's up to the person who's developing the ML model to choose the right set of features, and as people with physical insight working in engineering, you would know what variable is important, whether the temperature is important, or the number of cycles is important, or the pressure is important, or the concentration, or the processing condition, or the voltage, the potential, or the current, right. These are the kinds of variables that engineers we have a lot of physical insight into, and with that core domain knowledge we will be able to understand, right, what kind of features we will be using and whether those features are really the right ones. So DBSCAN unfortunately found only two clusters, although we know there are three types of flowers, so clearly one could do some kind of feature engineering here. So 71 points in the first cluster and 33 points are in the second cluster. Alright, so this is where we are plotting the clusters, right. So there are three types of flowers: setosa, versicolor and virginica, and these have been assigned different colors, and this is where we are plotting cluster numbers, right. We are looping through all the clusters and then plotting the 0th component of the cluster of the points in that cluster, and the first component, right, the first PC1 of the points in a particular cluster and the PC2 of the points in a particular cluster. Okay, so that's what the x and the y labels are, and let's see what we get here, right. So this is the DBSCAN clusters, right. So that's cluster 1, this is cluster 2, and this point has been relegated to noise, which is useful, right. If you want to do an outlier analysis, that's something useful, and these are the true species, right. This is setosa, this is versicolor, and this is Virginica. So you can see that the features that we have selected, and consequently even the principal components here, are not able to distinguish very effectively between these two types of flowers, and they have been lumped into one big cluster here. So clearly there's a need for feature engineering, and that's something which can be done and should be done. Alright, so let's of course also demonstrate DBSCAN with some more with some data where we can actually see different clusters, and not this kind of a scenario where some of the points are sort of getting lumped into the same cluster, although we know they are about different categories. So let's apply DBSCAN with a reasonable epsilon value and see how well it recovers the original clusters in a synthetic data set. So here we are using this make blobs function from sklearn.data sets, and we are making 750 samples, right, here with a given random state, and then of course we are applying the standard scalar to make the mean 0 and variance 1, and this is the plot, right, of the first two features 0 and 1. Alright, so this is what we are seeing here clearly, right. There are 3 blobs here, that is what we have used the make blobs function. Here we had actually specified the centers of the blobs, right. So that is where 1 1 minus 1 minus 1 and 1 comma minus 1, that is where the centers of these blobs are. We had also specified the standard deviation of every cluster, which is equal in this case to this value. Alright, so now with this data set, can DBSCAN recover the original cluster? So let's see. So here we have chosen the epsilon equal to 0.31. Again, you can make the kind of elbow plot that we did with the k nearest neighbors, and then see if that helps you. And here it is able to estimate 3 clusters, and of course there are some noise points here as well. Okay, so to recollect, epsilon is the maximum distance between 2 points to consider them as neighbors. If you make it too small, there will be too many clusters, and you won't really get physical insight. And if you make it too large, then there is one big blob, right. It's like saying that this is the data set of this particular problem. There's no insight from there. So again, since we don't know the right epsilon, we plot the distance to each point's kth nearest neighbor, and the idea is that clusters have consistent internal density, so their kth nearest distances will be small, while points near the boundary or noise will show a clear jump, which is what we saw in the previous example as well. And we need to look at the elbow in the kth distance graph, so that's what we are doing. We are importing the nearest neighbor module from sklearn.neighbors, and we are looking at the 10th nearest neighbor here, because we want each cluster to have at least 10 points, right. If you go back to where we implemented DBSCAN, we do specify the min samples, right. So that's the minimum number of samples in a region, right, for it to be recognized as one cluster, and that's the reason why we are looking at the 10th nearest neighbor and trying to find out how the distribution changes. Okay, so yeah, we are looking at the 10th nearest neighbor, and we get the distances to the 10th nearest neighbor, and then sort it and plot the number of points. So on the y axis is the distance to the 10th nearest neighbor, and then on the x axis these are the points sorted by distance, right. So as the distance to the 10th nearest neighbor increases, the number of points that get included that's also going to increase, right. And here there's about 750 points, right. If you remember, we had generated 750 samples here right at the top, so that's why you are seeing that the total number of points here is 750, right. So as you go to all the points, right, the distance to the 10th nearest neighbor is about 0.6, and you can see that somewhere around here, right, around 0.3 there is a big jump. So this is probably a dense region, right, if you consider these points, and then beyond that those are the sparse regions. So that's the distance you can consider. Okay, so considering 0.31 as the distance, and of course min samples is 10, that's why we were looking at the 10th nearest neighbor. If you want to change min samples, again that is possible, it's entirely up to you, and you see that there's 3 clusters which we obtained, right, and then there's also 16 noise points that we obtained. So let's finally visualize the data from the DBSCAN based clustering. Okay. So like I said, DBSCAN can identify different types of points, the core points, which are the large circles where there are points with enough neighbors within the epsilon distance. Then there are border points, the smaller circles where points with an epsilon of a co-point but don't have enough neighbors themselves, and then the noise points black, which don't belong to any cluster. So this is quite nice. We are able to plot all of these. Of course it will take some time for you to understand this code, what's happening here. So I encourage you to go into it. We are using different types of colors for the noise points, right, as well as the other points. So I encourage you to go slowly through this code and figure out what's happening, and we will make available the notebook as well, right. So these are the three clusters. You can see that these are the noise points, right, in black. Then the larger circle are the core points, and then the smaller circles are the non-core points. Okay. So this finishes our discussion of density based clustering. We will now move to nonlinear dimensionality reduction, and if you remember in the class we had looked at two different algorithms. One was t-distributed stochastic neighbor embedding and one was UMAP. So first let's get started with the t-SNE. So this is a powerful technique for visualizing high dimensional data, and it projects it into lower dimensions, right, and t-SNE reduces the number of dimensions while preserving the local structure. It's non-linear, so it can capture any complex relationships which are missed by principal component analysis, which is really a linear dimensionality reduction technique, and this t-SNE is great for visualization and is very good at revealing clusters. Alright, so here there is a key parameter that has to be used. It's called the perplexity, and is basically how many neighbors should each point consider. That's the parameter in t-SNE, and if you look at low perplexity, it focuses on very low structure, and high perplexity is more global structure. So you can try various values and see how it affects your visualization, right. So we are importing t-SNE from sklearn.manifold. We are trying various perplexity values, which I said is how many neighbors should every point consider, right, and then you can assign again different colors and labels to these points, and we are always looking at two components here because it's easy to visualize two components. Ultimately we want to plot the data in the space of the new space, the t-SNE space, and it's easy to plot if you have two components. So that's why we are sticking to two components. Alright, so let's see how these plots look, right. So these are the plots with 4 different perplexity values: perplexity 5, 10, 30 as well as 50. So you can see that if the perplexity is 5, right, then you are not able to capture enough of the structure, and therefore you are not seeing, right, how different these points are. If you increase the perplexity, right, then slowly more structure is starting to emerge. This is setosa, this is versicolor, and this is virginica, and then you can keep on doing it. At some point, of course, the benefits start to come down, right. In this case again these points sort of look very close in the t-SNE space, and therefore I mean it's not very useful if you increase the perplexity beyond a point. So this seems like a nice sort of trade off, right, not too high or not too low. So that's how you can figure out, right, what perplexity you should choose. Okay. And finally, if you want to implement UMAP, which is the most modern non-dimensionality reduction technique that we studied in this course, it stands for uniform manifold approximation and projection. It's a newer alternative to t-SNE, which is better at preserving the global structure. If you remember, the kinds of functions we were using to compute distances in t-SNE and UMAP is slightly different, and therefore it is able to preserve the global structure. The kind of the function that we were minimizing, in one case the KL divergence, in the other case the cross entropy, is also different. So because of the use of the cross entropy, the UMAP is better at preserving global structure and is less sensitive to hyperparameters and more scalable to larger data sets. So these are some of the advantages of UMAP. The key parameters here is the number of neighbors. Low values will focus on local structure and more detailed clusters, whereas higher values will preserve more global structure and broader kinds of patterns may emerge. So let's explore how different n neighbor values will affect our UMAP embedding. So of course you can use pip to install UMAP. If it's not already there, it's called UMAP learn, and once it's there you can import UMAP, and here we are specifying the color map and the types of flowers, the labels, and we are working with different types different numbers of neighbors 5, 15, 30 and 50, and then for each of these we are applying UMAP, right, with the number of neighbors specified. Number of components, like I said, just like we did with t-SNE, usually in these non-linear dimensionality reduction approaches you stick to just 2 components because it's easiest to visualize the data in those 2 components, right. So you do that and then you can plot, right, the UMAP component 1 on the x axis and UMAP component 2 on the y axis, and let's see what happens when you make this plot, right. So these are this is UMAP with n neighbors 5, the first one, right. There is some mixing of the flower types here. This is UMAP with number of neighbors 15. Again, I mean, we are not really able to make out the difference between these kind of flowers, the versicolor and the virginica here, and then when you make it 30, again you see that it's not really a problem with the dimensionality reduction technique, but it's more the kind of features that were originally there, right. If your original features are not good enough, then it's not going to be able to make much difference even if you do dimensionality reduction and so on and so forth, right. So this brings me to the end of this particular tutorial. We did discuss what happens when we do DBSCAN, which is density based clustering algorithm. We also looked at nonlinear dimensionality reduction via 2 different techniques, which are UMAP as well as t-SNE, which works slightly differently, right. t-SNE is the older variant that is based on preserving more the local structure. The UMAP also focuses on the global structure, but at the end of the day all these algorithms are only as good as the data and the features, right. So if you don't select your features properly, you may face some trouble. So I encourage you to spend some time thinking about your problem and engineering the features that would work the best. So thank you for joining today, and I look forward to seeing you next time.